The first sign of alien life may not be a fossil, a signal, or a creature, but a pattern hidden inside chemistry. It may arrive as a graph on a screen, not a face staring back from another world, not a skeleton under red dust, not a fish moving beneath the ice of Europa, not a radio message crossing the dark between stars, just a row of peaks, a strange distribution of molecules, a chemical fingerprint that seems ordinary until someone in the room realizes it should not look that way. A future spacecraft may carry that evidence home in a sealed tube. It may be a sliver of ancient Martian rock, drilled from a dry lakebed where water once moved through mud. It may be an ice grain caught from the plume of an ocean moon, a frozen speck from a sea no human eye has ever seen. It may be dust, salt, carbon compounds, broken fragments, and noise. It may look so unimpressive that no one outside the laboratory would understand why the room has gone quiet. But science often begins exactly there, not with a scream, with a suspicious pattern. The old dream of finding alien life was simpler. Find water, find organics, find oxygen, find methane, find the right molecule, and the case begins to look alive. For a long time, that was the public version of the search. Water meant possibility, carbon meant possibility, strange gases meant possibility. A world with an ocean under ice became a place of hope. A planet with ancient river deltas became a place where imagination could move in. But possibility is not evidence. Water does not prove life, organic molecules do not prove life, methane does not prove life, oxygen does not prove life. Even a molecule that living organisms make on Earth can be made by a world that has never had a single cell. That is the uncomfortable truth at the center of modern astrobiology. The universe is not chemically simple. It is not a quiet, empty stage waiting for biology to appear. It is already full of reactions. Stars build elements, meteorites carry carbon compounds, radiation breaks molecules apart and helps create new ones, minerals guide reactions on their surfaces, hydrothermal systems drive chemistry through heat, pressure, water, and rock. Icy grains preserve fragile compounds, atmospheres are altered by sunlight, lightning, volcanic gases, impacts, and time. A dead world can still make interesting chemistry. A lifeless ocean can still be chemically rich. A rock can contain carbon and water and ancient history, and still have nothing to do with biology. That is why the search has become more forensic. Scientists are no longer only asking whether a familiar molecule is present. They are asking what kind of world produced it. They are asking whether the full chemical scene makes sense without life. They are asking whether the evidence is just an ingredient, or whether it carries the marks of organization. A molecule is a clue, a pattern is a crime scene. That difference matters because life is not just a substance. Life is a process that changes substances on Earth. Living systems do not simply contain molecules. They select them, they arrange them, they amplify them, they destroy some and preserve others. They build membranes, pigments, metabolic products, waste products, genetic molecules, structural compounds, signaling molecules, and fragments of larger systems. They leave chemistry with a memory of use. Life does not explore chemical possibility evenly. It makes choices, not conscious choices, not design in the human sense, but selection, function, survival, and reproduction push chemistry in certain directions and away from others. Molecules that help a living system persist are repeated. Molecules that store information are protected. Molecules that form boundaries are used again and again. Molecules that help move energy become part of networks. Over time, biology turns chemistry into a history of what worked. A sterile reaction mixture may contain many compounds. A living system may leave behind chemical habits. That is what the new test is really about. Not a magic detector. Not a machine that flashes green when alien life is present. Not a shortcut around evidence. The new test is a way of asking whether chemistry has been organized by something more than geology, radiation, and chance. It is the search for a fingerprint without a hand. In a dark laboratory, that fingerprint would not look like a human print. It would look like molecular abundance. It would look like a distribution of compounds. It would look like families of related molecules appearing in suspicious ratios. It would look like a mixture that has diversity, but not the flat randomness of ordinary synthesis. It would look like complexity shaped by selection. The word selection is dangerous here, because it can make chemistry sound alive before the evidence earns that right. Non-living nature also. Minerals select ions. Crystal structures favor certain arrangements. Catalysts accelerate some reactions and not others. Temperature, pressure, acidity, salinity, radiation, and water activity all shape what molecules can form and survive. A lifeless environment is not random. That is why no chemical pattern can be treated as automatic proof. A strange distribution may be biological, it may also be geology wearing a mask. The new test does not solve that problem by ignoring it. It makes the problem the center of the investigation. Every exciting signal must face the same question: can this happen without life? If the answer is yes, the case weakens. If the answer is partly, the case remains open. If the answer becomes harder and harder after every serious non-living explanation is tested, the case begins to change. This is where the search for alien life becomes less like treasure hunting and more like forensic science. A detective does not solve a murder because one object is found in a room. A fingerprint matters because of where it is, what shape it has, whether it matches, whether it could have arrived innocently, whether it fits the timeline, whether it agrees with the rest of the scene. Blood on the floor is not a story by itself. A broken window is not a conviction. A footprint in mud is not a verdict. Evidence becomes powerful when it forms a pattern that the innocent explanations cannot carry. Astrobiology has reached that same level of suspicion. A single molecule is no longer enough, the whole scene has to speak. Mars is the planet that taught this lesson with a kind of cruelty. It is close enough to study and still difficult enough to resist certainty. From orbit, its surface carries the memory of water. Ancient valleys cut through the landscape. Deltas spread where rivers once flowed into basins. Minerals formed in the presence of water sit inside old rocks. Sediments preserve layers like pages in a ruined book. Mars looks like a world that once had rooms where life might have entered. But an empty room can still have a floor, a window, a chair, and dust. Habitability is not habitation. That sentence should hang over every claim about Mars. There may have been water. There may have been lakes. There may have been chemical energy. There may have been organic compounds. There may have been environments where microbes, if they existed, could have survived. None of that proves they did. A kitchen is not a meal. A lakebed is not a biosphere. A planet with the ingredients for life is not automatically a living planet. Still, Mars matters because it preserves the possibility of a case. Its ancient rocks may hold chemistry from a time when conditions were less hostile than they are now. Rovers have found organic molecules in Martian rocks. That is important, but it must be said carefully. Organic does not mean alive. In chemistry, organic mainly means carbon-containing. Carbon chemistry is essential to life as we know it, but carbon chemistry can also happen without life. Meteorites can deliver organic. Water and rock can produce organics. Heat and minerals can transform organics. Radiation can destroy organics and create confusing fragments. A rover can detect carbon compounds and still leave the central question untouched. Where did they come from? That is why context matters. A molecule found in an ancient lakebed means something different from a molecule found in windblown dust. A compound protected inside a fine-grained sediment means something different from one exposed at the surface for billions of years. Organic material associated with certain minerals may be better preserved. Organic material found in a pattern across a rock texture may be more interesting than the same material smeared randomly. The molecule is not alone. It has an address, and the address changes the meaning. Imagine a sample from Mars sealed inside a return capsule. It lands on Earth, is recovered, and enters a laboratory built to treat the rock as both treasure and threat. Not because anyone expects monsters inside, but because contamination could destroy the truth. Earth is covered in life, sheds biology constantly: skin cells, oils, microbes, laboratory residues, plasticizers, solvents, dust, and cleaning agents can all become false witnesses. The first commandment of alien life science is simple. Do not contaminate the crimes. The sample is opened. Not at once. Not all at once. Not carelessly. A thin section cut. A fraction is heated. Another is dissolved. Another is placed under instruments that can map minerals and molecules together. The rock is no longer just a rock. It becomes testimony. A mass spectrometer breaks compounds into charged fragments and separates them by mass. A microscope maps textures. Spectrometers identify minerals. Isotope measurements ask whether atoms carry unusual ratios. Each method sees a different part of the scene. None of them sees life directly. The question is whether the pieces converge. Do organics appear in a mineral setting that once held water? Are they concentrated in certain layers or textures? Do they form molecular families? Are their abundance patterns unusual? Can known Martian chemistry explain them? Could meteorites have delivered them? Could radiation have altered them? Could Earth contamination have introduced them? Could the instrument have created the pattern? Every answer either closes a door or opens a darker hallway. This is why the first true evidence of alien life, if it ever comes from Mars, may not look like a fossil. It may be a stubborn collection of chemical relationships, a pattern in organics, a pattern in minerals, a pattern in isotopes, a pattern that appears again when another lab tests another fraction, a pattern that is not destroyed by the obvious explanations. That does not mean life is declared, it means the pressure increases. The pressure is the story. A weak clue asks for attention. A strong clue asks for explanation. A dangerous clue makes the ordinary explanations begin to fail. Mars is not the only crime scene farther out. Beyond the warmth that shapes Earth and Mars, ice becomes the door to another kind of world. Europa and Enceladus look frozen from the outside, but their importance lies beneath the crust. Their surfaces are not the whole story. Under ice there may be oceans, under oceans there may be rock. Between water and rock there may be chemistry, and where chemistry is driven by energy, life becomes a question that cannot be dismissed too quickly. But again, water is not life, an ocean under ice is not a biosphere, a hidden sea can be sterile. That is what makes these moons so compelling and so difficult. They offer the environment that life might use, but not the proof that life has used it. A dark ocean may contain salts, organics, chemical gradients, hydrothermal activity, and still remain lifeless. Or it may contain biology that has never seen sunlight, biology that would look nothing like the creatures imagined in old science fiction. If such life exists, it may not be captured as a swimming organism. It may not be photographed. It may not be visible through kilometers of ice. It may reveal itself only through chemistry leaking into space. Enceladus gives science an almost unbelievable opportunity. It sprays material out. Plumes rise from fractures near its south pole, launching water vapor and ice grains from somewhere below the surface. A spacecraft can fly through those plumes and sample material from an ocean it never enters. It sounds like a confession. It is not. A plume is not a clean message. It is a disturbed messenger. Ice grains form under specific conditions. They carry salts and compounds. They are accelerated into space. They may be altered, fragmented, or sorted. A spacecraft striking them at high speed changes them again. Instruments turn them into signals, and those signals have to be reconstructed into chemistry. Even when an ocean throws evidence into the sky, meaning does not come with it. A future probe may fly through a plume and detect organic compounds. That would be extraordinary. It would not prove life. It may detect molecular diversity. That would be more interesting. It may find patterns that look unusual compared with known non-living chemistry. More interesting still. But the investigation would still have to ask whether ocean chemistry, hydrothermal reactions, radiation processing, plume physics, instrument behavior, or contamination can explain the result. The most important word remains can. Can non-living chemistry do this? That question protects the discovery from becoming a myth. Europa is colder in the imagination, heavier, more silent. Its ocean is buried under an ice shell. Its surface is blasted by the radiation environment around Jupiter. Material on the surface may have been altered by particles and energy. If ocean material reaches the surface through cracks, chaos terrain, or possible plume activity, it may carry chemical clues, but those clues may be damaged before any spacecraft measures them. Radiation can erase evidence. Radiation can also create new chemistry, so a future Europa sample would arrive already complicated. A molecule found on the surface may not be original ocean chemistry. It may be an altered remnant, it may be a surface product, it may be mixed with salts, it may be changed by charged particles. To read it correctly, scientists need to know the local geology, the exposure history, the ice dynamics, and the broader environment. Europa is not a simple ocean waiting to be tested. It is a world where every clue has passed through a harsh filter. That is why missions that study habitability are so important. A mission does not need to declare life to matter. It can map the crime scene. It can identify regions where ocean material may be fresh. It can study its composition, geology, radiation, surface chemistry, and possible exchange between ocean and surface. It can make the next investigation smarter. Habitability is the map. Life detection is the case. Without the map, the case wanders. The idea of chemical patterns links Mars, Europa, Enceladus, and exoplanets because it changes what scientists are looking for. They are not only searching for one famous compound. They are asking whether chemistry has been pushed into a form that looks like use. That word is important. Use. Life uses chemistry. It pulls energy through matter. It builds boundaries. It stores information. It repairs damage. It reproduces. It leaves waste. It makes some molecules common and others rare. It produces related families of compounds because living systems are networked, not isolated reactions. A non-living environment can be complex. A living environment may be complex in a way that has purpose without intention. That sounds strange, but it is exactly what biology does. A cell does not think about its chemistry, yet its chemistry is organized around survival. Molecules appear because they do something. They persist because they help a system persist. They are copied, repaired, replaced, recycled, or discarded. The result is a chemical world shaped by function. A dead world makes products. A living world makes products that belong to a system. If alien life is very different from Earth life, the exact molecules may not match ours. It may not use DNA. It may not use proteins in the same way. It may not use familiar membranes. It may not even use the same biochemical strategies we expect. But if it is alive in any meaningful sense, it must maintain itself against decay. It must preserve some pattern through time. It must use energy. It must create differences that matter. Those demands may leave traces, not Earth traces, life traces. That is the hope behind agnostic biosignatures. They are called agnostic not because they assume nothing, but because they try not to depend too narrowly on one version of biology. Instead of asking only whether a sample contains molecules specific to Earth life, they ask whether the sample shows broader properties associated with living systems: complexity, organization, selection, disequilibrium, information like structure, and chemical distributions that are hard to produce without biology. It is a careful idea, not a miracle. It does not free science from assumptions. It does not make alien life easy to detect. It does not remove the need for context. It does not turn every strange pattern into proof. It simply widens the search beyond Earth's exact biochemical vocabulary. That widening is necessary because Earth is both our only teacher and our greatest bias. Every living thing we know belongs to one planet. Every confirmed biosignature comes from here. Every organism shares deep chemical ancestry with every other organism. Earth has taught us what life can do, but not all that life could be. If we search only for Earth copied elsewhere, we may miss something stranger. If we search for anything strange, we will fool ourselves. Forensic astrobiology lives between those dangers. It needs imagination sharp enough to recognize unfamiliar life and skepticism sharp enough to reject false patterns. This is where molecular complexity becomes more than a phrase. In ordinary speech, complexity can mean almost anything. In life detection, it has to be measured carefully. Some molecules are simple. Others contain many atoms arranged in specific structures. Some mixtures contain a few compounds. Others contain broad families with subtle relationships. Some distributions arise naturally from known reactions. Others may require repeated selection and maintenance. Life tends to create complex molecular systems because it is itself a network of processes. But non-living chemistry can also create complexity. That is why complexity alone cannot convict. A meteorite may contain a rich mixture of organic molecules. A hydrothermal may drive complicated reactions. Space chemistry can build carbon compounds under harsh conditions. Complexity raises interest. It does not close the case. The question is organized complexity. Does the sample contain many molecules in a pattern that suggests selection? Are certain families favored? Are molecules related in a way that resembles network chemistry? Do abundance distributions look unlike known abiotic baselines? Is the pattern tied to a plausible environment for life? Does it appear repeatedly? Does it survive contamination checks? Does it agree with other evidence? That is the chain. Break enough links, and the case collapses. Strengthen enough links, and the case becomes harder to ignore. The public often wants a single decisive sign because single signs are easy to understand. A fossil is easy. A signal is easy. A creature is. A molecule called a biosignature sounds easy, but real biosignatures are rarely simple because planets are complicated. A biosignature is not a sticker that says life was here. It is a sign that may have been made by life if other explanations. That if is the entire field. Oxygen on Earth is biological in a deep sense, but oxygen elsewhere can have non-biological pathways. Methane can be biological, geological, or chemical. Phosphine became famous because it is associated with life in some contexts, but the debate around it showed how difficult atmospheric interpretation can be. Amino acids are used by life, but they can also form in non-living chemistry. Fatty acids can be related to membranes, but some can arise abiotically. Organic complexity can be suggestive, but not automatically biological. Every famous clue has a shadow. The new test tries to read the shadows as well as the clue. It asks not only what was found, but what else should be there. If life made this molecule, what related molecules might appear? What patterns of abundance would be expected? What waste products, precursors, degradation products, or environmental signals should accompany it? If geology made it, what minerals or conditions should be present? If radiation made it, what alteration products should appear? If contamination made it, where should the same compounds show up in controls? A serious life detection claim must be surrounded by questions. That is not weakness. That is how the claim becomes strong. In the dark lab, the most exciting moment may not be the first strange peak. It may be the 10th failed attempt to explain the pattern without life. A scientist may be more frightened by stubborn evidence than by dramatic evidence. Dramatic evidence can be theatrical. Stubborn evidence changes careers. The first analysis shows a strange distribution. The blank run is clean. The second instrument sees a related pattern. The mineral map fits a once wet environment. The isotope data adds pressure. The contamination history does not explain it. A geological model explains part, but not all. A radiation model explains part, but not all. A meteorite delivery model explains part, but not all. The case does not shout. It tightens. That tightening is the true suspense. It is the slow narrowing of ordinary possibilities. A future discovery may unfold like that. Not one press conference. Not one photograph. Not one headline. That accumulating pressure. A paper says the chemistry is unusual. Another team challenges it. A third team repeats the analysis. A simulation tries to reproduce it. A mission finds a related pattern elsewhere. Skeptics become more specific. Supporters become more cautious. The language changes slowly. Interesting, unusual, difficult to explain, consistent with biological processes, not yet explained by known abiotic pathways. Those phrases may sound weak to the public. They may be the staircase to the most important conclusion in science. Science rarely moves from ignorance to certainty in one leap. It moves by making wrong explanations harder to keep. The search for alien life will be no different. The first real case may be messy, disputed, and slow. It may produce arguments that last years. It may frustrate people who want the universe to answer in a single sentence. But the universe is not required to speak clearly. It may only leave evidence. The most responsible scientists will treat that evidence with hostility. They will try to destroy their own favorite explanation. They will ask whether the pattern could be contamination. They will ask whether the instrument created it. They will ask whether a lifeless ocean could do it. They will ask whether a mineral surface could do it. They will ask whether a rare geochemical pathway has been missed. If the evidence breaks, it was not enough. If it survives, the survival matters. A false positive is not a failure if it teaches the field how not to be fooled. It becomes a warning. It sharpens future missions. It teaches which molecules are ambiguous, which planetary environments create traps, which instrument signatures are misleading, and which patterns are too easy to imitate. Astrobiology must become expert in non-life before it can claim life. That may sound backwards, but it is essential. Every non-biological process is an alibi. If the alibi works, life is not needed. If the alibi fails, the investigation deepens. The stronger the knowledge of geology, chemistry, atmosphere, radiation, and contamination, the more meaningful a surviving biosignature becomes. The search for life is also a search for every way nature can imitate life. This is why the new alien test cannot be separated from laboratory work on Earth. Scientists need to study living samples, dead biological samples, ancient samples, degraded samples, meteorites, hydrothermal products, radiation-processed ice, Mars-like sediments, salty brines, and synthetic prebiotic chemistry. They need to know what real biology looks like after it has been damaged, buried, fossilized, irradiated, and fragmented. They also need to know what lifeless chemistry looks like when it becomes surprisingly rich. Only then can a sample from another world be judged. Earth is the training ground, but it is also the trap. If all training data comes from Earth, a model may learn Earth-specific biology rather than life in a broader sense. If scientists only compare alien chemistry to familiar life, they may miss something radically different. If they make the criteria too broad, they may classify complex geology as biology. The line is narrow, too narrow, and alien life escapes detection. Too wide, and every strange rock becomes alive. That tension is why machine learning is both promising and unsettling. A computer can analyze patterns too complex for the human eye. It can compare thousands of signals in a chemical mixture. It can detect subtle relationships in molecular fragments. It can help separate living from non-living samples in experiments. It may find structure where human observers see only noise. But a machine is not a verdict. A model can learn contamination. It can learn the instrument. It can learn the laboratory. It can learn the difference between sample preparation methods instead of the difference between life and non-life. It can become confident for reasons that have nothing to do with biology. If no one understands what features drive the classification, the result becomes another mystery, not a solution. An alien life claim cannot rest on a black box. The model can become a witness. It cannot become the judge. Every witness must be cross-examined. What features did the model use? Molecular complexity, fragmentation patterns, abundance distributions, specific chemical family relationships among compounds, or hidden artifacts from the dataset. Does the model work on samples it has never seen? Does it fail honestly when tested against difficult abiotic chemistry? Does it generalize beyond Earth's biological patterns? A useful machine learning system would not replace scientific interpretation. It would help identify suspicious chemical scenes. It would point to patterns worth investigating. It would increase pressure, not deliver final truth. That is enough. In a field this difficult, better suspicion is progress. The future life detection mission may be built around that kind of suspicion. Not one instrument, not one signal. A suite of measurements designed to preserve context. A mass spectrometer for molecular mixtures, mineralogical tools to understand the rock or ice, imaging systems to locate textures and structures, instruments for salts, redox chemistry, and environmental conditions. Contamination controls woven into the mission from the beginning. The mission would not ask a sample one question. It would interrogate it from many directions. This is how the evidence may become strong enough. A molecule found by one instrument is fragile. A pattern found by multiple measurements is stronger. A pattern tied to a specific geological setting is stronger still. A pattern that survives contamination control becomes more serious. A pattern that resists non-biological explanation becomes dangerous. Dangerous in the scientific sense, dangerous because it may force a conclusion no one should reach too easily. There is an emotional discipline in this. The idea of alien life is so powerful that it pulls language toward exaggeration. A possible biosignature becomes life found in headlines. A chemical consistent with biology becomes alien microbes. A habitable environment becomes living world. The gap between scientific caution and public excitement can open in seconds. That gap is where false certainty grows. A mature story about alien life has to resist that. It must keep the wonder, but not let wonder become evidence. It must make the audience feel the pressure without pretending the case is closed. It must show why a chemical pattern could matter and why it might still be wrong. The strongest tension is not between believers and skeptics. It is between evidence and desire. Human desire wants the universe to be alive. It wants Mars to have had microbes. It wants Europa's ocean to contain something moving. It wants Enceladus to be more than water and salts. It wants a distant planet's atmosphere to carry the breath of a biosphere. That desire is not foolish. It is human. It comes from the ancient loneliness of looking up, but desire cannot analyze a sample. Evidence must do that. The evidence may be disappointing at first. It may be small. It may be technical. It may be a table of molecular features or a spectrum that only specialists understand. But the emotional weight is hidden inside the technical detail. If a pattern points toward life, then the universe has done something beyond scenery. It has organized matter somewhere else. It has crossed the boundary from chemistry into biology beyond Earth. That boundary is the deepest mystery. Where does chemistry become life? On Earth, the crossing happened so long ago that the original evidence is damaged. Life has been here for billions of years, reshaping the planet that gave rise to it. Plate tectonics recycled crust, impacts altered surface, erosion destroyed rocks. Biology itself overprinted earlier chemistry. The beginning is hidden behind everything that came after. Other worlds may preserve different parts of the story. Mars may preserve ancient environments that Earth has lost. Icy moons may preserve ocean chemistry under protective shells. Meteorites may preserve organic pathways from the early solar system. Exoplanets may show atmospheric consequences of biology on planetary scales. None of these places is guaranteed to hold life, but each may teach us where the boundary lies. The new test is not only a way to find aliens, it is a way to study the edge between non-life and life. That edge may not be clean. Life may not begin as a sudden spark. It may emerge through networks, cycles, compartments, replication, selection, and increasing organization. Before biology, there may be chemistry that looks almost biological. After biology dies, there may be residues that look partly geological. The line may be smeared by time, environment, and preservation. That makes detection harder. It also makes it richer. A sample may not prove life, but it may show prebiotic organization. It may show that chemistry on another world moved toward the conditions life needs. It may show that organic complexity is common, but biology is rare. Or it may show that once chemistry reaches a certain threshold, life becomes difficult to avoid. Any of those answers would change the way we understand Earth. If Mars was habitable but lifeless, Earth becomes more unusual. If Mars once had life, then life may arise more easily than we thought. If icy moons contain life in dark oceans, then sunlight is not the only doorway to biology. If exoplanet atmospheres show patterns best explained by biospheres, then life may be a planetary phenomenon across the galaxy. But all of those possibilities depend on evidence that can survive. This is why the image of the cosmic crime scene works so well. It strips away the fantasy. No glowing aliens, no instant answers, just a table, a sample, a screen, and investigators who know the cost of being wrong. On the table lies a fragment of another world, in the screen lies a pattern. Around the pattern stand every innocent explanation science can imagine. The work is to see which ones remain standing. A molecular fingerprint is not the organism. It is the trace left by contact. Life may not be present in the sample anymore. It may have lived long ago. It may have degraded. It may have left fragments. It may have altered minerals, change-produced organics, shifted distributions and disappeared. If the organism is gone, only the consequences remain. That is not so different from paleontology, but the evidence is smaller and less forgiving. A dinosaur bone preserves shape. A microbe may leave texture. A chemical biosignature may leave no recognizable form at all. It may only leave relationships among molecules. A fossil asks the eye to recognize structure. A chemical pattern asks the mind to recognize process. That is harder. It is also more universal. A fossil depends on bodies. A radio signal depends on intelligence. A creature depends on being visible. A chemical pattern may be by life that is microbial, hidden, ancient, or unfamiliar. It may be the only kind of evidence we can reasonably expect from many worlds. The first life beyond Earth may not be discovered by seeing life. It may be discovered by seeing what life did. That possibility changes the meaning of exploration. A spacecraft flying through an icy plume is not just collecting particles, it is sampling a hidden ocean's history. A rover drilling Mars is not just grinding rock. It is opening a sealed environment from billions of years ago. A telescope studying an exoplanet atmosphere is not just measuring gases. It is asking whether a whole planet is out of chemical balance in a way life could explain. Every mission becomes an interrogation. Every sample becomes a witness. Every pattern becomes a possible testimony. But testimony can be false. That is why repeated measurements matter. A one-time signal is fragile. It may be noise, contamination, instrument behavior, or a transient process. A repeated signal becomes harder to ignore. A pattern seen across multiple samples, multiple methods, or multiple times begins to build weight. It may still be non-biological, but it requires a stronger non-biological explanation. Science does not need the first clue to be conclusive, it needs the clue to lead somewhere. A suspicious pattern can guide future missions. It can tell scientists where to sample next. It can reveal which instruments are needed. It can change mission priorities. It can show which environments preserve organic complexity and which destroy it. It can refine the search even if it never becomes proof. In this sense, even ambiguity is useful. A good mystery teaches you where to look again. There is a darker possibility too. Maybe every promising pattern will fail. Maybe Mars has organics but no biology. Maybe Enceladus has rich ocean chemistry but no life. Maybe Europa has energy and water but no living system. Maybe exoplanet atmospheres will produce false positives again and again. Maybe the universe makes ingredients easily and life rarely. That outcome would be haunting. It would make Earth feel less ordinary. It would suggest that the step from chemistry to biology is harder than hopeful headlines imply. It would turn every habitable environment into a reminder that possibility is not enough. It would make the silence more meaningful. But even then, the search would not have failed. It would have measured the difficulty of becoming alive. There is another possibility. Maybe life is common but usually hidden. Not in cities. Not in creatures large enough to see, but in microbial systems under ice, inside rocks, beneath crusts, or in oceans sealed away from stars. Maybe the galaxy is not silent because life is absent, but because most life never builds a transmitter, never grows a forest, never makes a fossil big enough for our imagination. Maybe the universe is alive in a small way, a chemical way, a way that must be detected by patterns rather than pictures. That would be stranger than science fiction, because it would replace spectacle with subtlety. It would mean we have been looking for a shout when the evidence is a whisper. It would mean life's most common signature is not intelligence, but organization, the organization of matter against decay. That is what all life does. It resists the drift toward disorder, not forever but long enough to reproduce. It holds chemical systems away from equilibrium by moving energy through them. It builds boundaries, copies information, repairs damage, and leaves being traces of these activities. When life dies, the traces fade, but they may not vanish immediately. In the right environment, some remain. A mineral surface may protect them, ice may trap them, sediment may bury them, salt may preserve them, a rock may carry them across billions of years, a plume may launch them into space, a telescope may catch their atmospheric consequences from light years away. This is the deep reason a chemical pattern could matter. It is not because patterns are mysterious. It is because life is a pattern-making process. It does not merely exist in matter. It organizes matter through time. The challenge is proving that a given organization came from life. That challenge will not be solved by excitement. It will be solved by better baselines, better instruments, better missions, and a more disciplined public language around discovery. The word biosignature must be handled with care. It does not mean proof. It means a possible sign of life. A possible sign can be strong or weak, direct or indirect, ambiguous or compelling. The strength depends on context. The same chemical may be more meaningful in one environment and less meaningful in another. The same pattern may be suggestive in a protected sample and meaningless in a contaminated one. A biosignature is not a verdict. It is an argument. The argument has to be built. For Mars, the argument would include geological history. Was the sample from an environment that once had water? Did it preserve fine sediments? Were organics protected from radiation? Are the molecules indigenous to Mars? Do they appear with minerals that make sense? Are isotopes unusual? Can abiotic pathways reproduce the distribution? Are similar patterns found elsewhere? For Enceladus, the argument would include plume dynamics, ocean chemistry, salts, organics, particle formation, hydrothermal possibilities, and repeated flyby measurements. Are the molecules coming from the ocean? Are they altered in transit? Are their distributions consistent across plume samples? Can non-living ocean chemistry explain them? For Europa, the argument would include ice geology, radiation, surface ocean exchange, salts, oxidants, possible fresh exposures, and the survival of molecules under harsh surface conditions. Are detected compounds original, altered, or produced at the surface? Does their context point downward toward the ocean or outward toward radiation chemistry? For exoplanets, the argument would include atmosphere, star type, planetary history, climate, surface conditions, photochemistry, volcanic gases, ocean loss, and combinations of gas. Does the atmosphere contain disequilibrium that is hard to maintain without life? Or can the star and planet produce it naturally? Every world has its own courtroom. The evidence cannot be copied from one to another. That is why the new alien test is not one universal answer. It is a framework. It tells scientists to look for organization, but it does not allow them to ignore environment. It tells them to value molecular patterns, but not worship them. It tells them to search beyond Earth-specific molecules, but not abandon skepticism. The best version of the method is cautious enough to be trusted and imaginative enough to matter. The worst version would become another hype machine. A video title can say new test. A thumbnail can say alien life test, but the science underneath must remain honest. No test can simply prove aliens. No molecule can end the debate alone. No pattern can replace independent evidence. The excitement comes from the possibility that we may be learning how to ask the question in a deeper way. Not did we find the right molecule? But did something organize this chemistry? That question feels almost alive by itself. It points toward a future where the first evidence of life may be read like forensic residue. A sealed tube from Mars enters a laboratory. Ice grains from an ocean moon are captured by a probe. A telescope detects a strange atmospheric mixture. In each case, scientists do not leap to biology. They build the scene. They test the scene. They try to break the biological interpretation. If it breaks, the universe remains silent for now. If it survives, the silence changes. The emotional center of this story is the moment before anyone says the word life. The screen glows. The sample is gone, consumed by analysis. The data remains. The pattern is not enough, but it is not nothing. The room is full of people trained to doubt themselves. They know that an error here would echo through history. They know that a true result would echo even longer. So they do not celebrate, they interrogate. That is what makes the discovery worthy of belief. A weak story needs certainty at the beginning. A strong case earns it at the end. The first sign of alien life may be hidden inside chemistry because chemistry is where life begins, works, and leaves its traces. It may not give us a face. It may not give us a message, it may give us a pattern that forces every non-living explanation to struggle. That is enough to change the search. The old imagination looked for creatures. The new investigation looks for consequences. A fossil says something lived here. A radio signal says something may be speaking. A chemical pattern says something may have organized matter here. That last message is quieter, but it may be the one we are most likely to receive. On a dead world, chemistry can be rich. On a living world, chemistry carries history. The difference may be subtle, it may be damaged, it may be hidden in a spectrum, a ratio, a molecular family, an abundance distribution. It may require instruments, models, debates, and years of doubt. It may frustrate every easy answer, but if the pattern is real, and if it survives, it may become the most important clue ever found. Not because it looks like life, because nothing else can explain it well enough. That is how the first discovery may begin, not with a creature moving under alien ice, not with a radio voice from another star, not with a fossil held up to a camera, with a chemical scene that refuses to stay innocent, with a molecular fingerprint on a dark screen, with a question whispered in a laboratory where no one is ready to say the final word. What process made this? If the evidence is weak, the answer will be chemistry. If the context is wrong, the answer will be geology. If the controls fail, the answer will be contamination. If the models improve, the mystery may disappear. But if the evidence remains, if the pattern repeats, if the context fits, if the alternatives fail one by one, then the quietest clue in the room may become the loudest discovery in human history, a hidden pattern, a chemical trace, a world that may not have been dead after all.